Good morning, physics class. Welcome to problem set 35, your final physics problem set. It's hard to believe we're here, and I really didn't plan on doing this online, but I guess that's what we're going to be doing. So today we're going to be talking about speed of sound. We've already had some work where we've been working on the speed of light. Today we want to incorporate speed of sound. Let's just say that we have a situation where we had someone firing a gun. Let's call this guy Bill. And he's got a gun and he fires that gun, that bullet, this direction. And there is an observer. Say he's way over here. And what happens is the sound waves travel towards him, but so do light waves. We know we've experienced this inductively that light travels faster than sound. But now we want to use a little bit of deduction to incorporate the difference between the two and get a little bit better understanding. So what we say here is that when he sees with his eyes the light flashing, then it takes 6.5 seconds for him to hear the sound. So maybe he's sitting here. This is something that you've probably done with lightning and thunder, where you count 1 1,000, 2 1,000, 3 1,000. So you can tell how far away the lightning was. And so this is kind of the concept behind that, because you're going to see the action before you are going to hear the action. One of the things that I have provided with you in this problem set is a chart about speed of sound, and that'll be something that you'll want to refer to, especially on the next slide. I'm going to have to get my chart out. But it says here, no, just picture in your mind. You see it instantly, but then it might take a little bit for you to hear the sound coming. And if it took 6.5 seconds, so you're sitting there going 1 1,000, 2 1,000, 3 1,000, and it takes 6.5 seconds, how far are you away from what's taking place? This is a kind of a neat thing that you can do, and it's just based on like everything else that we have done this year. It's based on simple unit analysis. So if we say that the speed of sound is 300 is on average. Now it varies a little bit. When temperature has a big bearing on it, but on average about 350 meters per second. And it took 6.5 seconds. You can look. This is even kind of a simple unit analysis problem. How far were you away? So you do 350 times 6.5, and you can see your seconds cancel out, and you are 2,275 meters away, or 2.3 kilometers. So, but then the question kind of comes, okay, well, if that's how fast would the light get to your eyes? Kind of to compare, we can use unit analysis again. So we know that the distance from the action to the observer is approximately 2,275 meters. In just a minute, we'll round that to proper significant digits. But the question is how long would it take the light to get there? Well, we can use a reciprocal unit analysis in order to solve that part of the problem. I know it's not asked in the question, but I'd like us to understand the concept. So if we have 2,275 meters, and light travels at 3 times 10 to the 8th meters per second. Do you see how I just took that formula unit and I took a reciprocal of it? So now my meters cancel, and the only thing that's left is seconds. So I'll take my 2,275, and I'm going to carefully on my calculator. Actually, I'm going to write this out for you. what I'm going to do is I'm going to say 2,275, and just so there's no mistakes, I'm going to say divided by 3 times 10 raised to the 8th power, so that no order of operations gets messed up as I'm trying to do this, okay? So times 10 raised to the 8th power, I get that it would take 0.00007583 seconds for the light to travel from the gun to the eye. You know, there's a verse in the Bible that talks about in the moment, in the twinkling of an eye. And I just think about that. It sounds like the speed of light was at play in that, it will be at play in that particular prophecy given by the Apostle Paul. Okay, and that would be the time it takes for the light to travel from the action to the observer. But the question up here asks is, how far away was the hunter from the observer? Well, the solution that I want to kind of put as my actual answer for your homework purposes and stuff has 3 significant digits. So I'm going to say it's about 2,280 meters approximately. Okay? Any questions? Let me know. But let's move on and we'll do another speed of sound problem. And this one, please never, never, never try this at home. This is just for illustration purposes only. I think I need to put fair warnings out about some of these physics problems. But this is we're about to teach a concept. It says a very reckless, foolish daredevil puts his ear to the rail of a railroad track and saw steam coming from the whistle of the train 1,300 meters away. On average, the speed of sound in air is approximately 350 meters per second. Again, I want to preface that can change. One of the big factors is based on temperature, and the chart that I provided explains some of that, so you can look into that. But it says, did this foolish daredevil, did he hear the train in the air first, or did he hear it in the iron rail first? At what time did he hear each sound? So we got a free body diagram. And on our free body diagram, we got a set of railroad tracks with an oncoming train that's got some steam coming out of it. And chugga, 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 choo, choo. And then this young guy, foolish daredevil, puts his ear down to the train track. The sound can travel through 2 mediums. It will travel through the air, and it will also travel through the iron rail. It will travel at a different speed through each one, reaching the ear of the observer. So first of all, let's take a look and let's calculate the time it will take for the sound to get to his, again, if we start with 1,300 meters away, and we use a reciprocal formula unit. So that means we're going to do 350 meters per second. So if the speed of sound in air is 350 meters per every second, we can reciprocate that and in order to make it fit the particular need in this problem. Meters cancel, so we'll take our 1,300 meters and divide it by 350 of the meters per every second, and we're going to get that this sound in the air will take 3.7142857 seconds for it to reach him. And now I'm going to get out the chart that I provided you on this lesson, and you will see that there's a different speed of sound for velocity of sound in iron is equal to 5,120 meters per second. So we can put that into a unit analysis problem. There's 1,300 meters away, and it's 5,120 meters every second in iron. Now you should be able to see what's going on here. So we go 1,300 divided by 5,120. It's going to take a quarter of a second for it to travel through the iron. Very, very different than how long it takes in the air. So he will hear it from the iron first, and the speed or the time it took in air, figuring it in two significant digits, is 3.7 seconds. And that's in the air. And the time on the iron is 0.25, a quarter second in the iron. Were you shocked by those answers? I hope that kind of made a little bit of, helps you understand the concept a little bit better. All right, let's move forward. Let's go back to last week's problem set and review that in our incremental development of physics. And so what we want to do is we want to calculate if you had silver at the melting point of water, 0 degrees Celsius, its fiducial point, and you were to raise it to the point at which silver liquefies at 960.8 degrees Celsius, how much energy would it take to melt that silver? I'm putting these up there sometimes. You guys know I forget to change things once in a while, but that should be silver, okay? So what we're going to do here is we will start with the specific heat of silver, 234 joules per kilogram Celsius. I have 21.35 kilograms, and I am changing it 960.8 degrees Celsius. The kilograms cancel, the degrees Celsius cancel, and that should tell me the amount of joules that it takes to increase the temperature of the silver, those 960 degrees Fahrenheit times 960.8. So the grand total for the change in temperature was 480,060,772 joules. But then we also need to take into consideration the latent heat of fusion, the energy it takes to actually make the phase change from a solid to a liquid. So we're going to start with that formula unit of 88.3 times 10 to the third joules per kilogram. And what I want to do is I want to cancel out the kilograms, 21.35 kilograms. That will cancel out the kilograms, and all that will be left with is joules. So we'll do 10 to the third power times 88.3 times 21.35 gives me a grand total of 188,885,205 joules. And then we'll add that to what we had to change the temperature. And we'll get a grand total of the amount of joules that it takes is 668,527 65.72 joules. Now we can take and put our significant digits into the problem. I see 3 in the problem. Let's not worry too much about this 0 that we had. No, actually we probably should. We should, because it says it's at 0 degrees. I should have put in more significant digits if I wanted them. So 7 times 10 to the 1, 2, 3, 4, 5, 6th power joules. That would be our solution. Okay, let's move on. One more problem for today. It says the period of light is 4.34 times 10 to the negative 10th seconds. Find the frequency, find the wavelength of this ray in a particular medium if the medium has an index of refraction of 1.780. So there are some formulas that we need to know. Do you know what they are? One of them is N equals C over V. F equals 1 over T. And V, excuse me just a second, V equals F lambda. N stands for index of refraction. C, speed of light in a vacuum. V, speed of light in a medium. F equals the frequency of that light. T is the period of the light, how often it repeats. And lambda is wavelength of the light wave. All right? So we can use these things in order to help us solve this particular problem. So the first thing it says is find the frequency. Frequency, again, is found by F equals 1 over period. And we know that the period is 4.34 times 10 raised to the negative 10th seconds. Okay, so we'll do that on the calculator. 10 raised to the negative 10th times 4.34. And then we're going to do 1, the reciprocal, that ends up being a reciprocal of that. And so we get F, the frequency, equals 2,304,14,7465 hertz. So then it says we also need to find the wavelength, so we'll be using this formula here, but before we do that, we need to calculate the speed of light in this particular medium. In order to do that, we're going to use the formula N equals C over V, and N value is 1.780, says it right there. Speed of light in a vacuum, we've already talked about that today, 3 times 10 to the 8th meters per second. And that will allow us to find the speed of light in this particular medium. So we'll do 1.780 times V equals 3.08 times 10 to the 8th. We're going to divide both sides by 1.78. So we'll get 3.0 times 10 to the 8th divided by 1.78. So 3 times 10 to the 8th divided by 1.78 gives me a velocity speed of 1.6854 times 10 to the 8th meters per second. So now we can put that value with our frequency into the equation that will allow us to find wavelength. So we're going to get 1.6854 times 10 to the 8th meters per second equals 2,304,14,7465 times lambda. So when we put that into our handy dandy calculator, 7465, sorry, I'm just double checking. You should double check too. I get 0.073 meters. That's actually not a very long wavelength. So then when we take a look at, we had 3 significant digits in the problem. I'll put one more in there. So the solutions from my calculator, I didn't make it up out of thin air. I got that off of my calculator. Frequency equals 2.30 times 10 to the, just check, double check, 1, 2, 3, 4, 5, 6, 8, 9th power, 10 to the 9th power hertz. And the wavelength equals 7.31 times 10 to the negative second meters. All right. Hopefully these helped you. Get ready for this week's homework and this week's quiz. Have a great day. Thank you so much.